For about as long as humans have been doing philosophy and science, we've been wondering about this question. That is, can we chop up an object forever? If we took an infinitely sharp knife and we put it to some object, say this piece of carbon here, this piece of graphite, and we tried to cut it in half, and then cut it in half, and then cut that in half, and on, would we eventually get to some uncuttable, indivisible, fundamental particle? Or do we just keep going on and on, like that fractal GIF there? The Greek philosopher Democritus thought that we did get eventually to some fundamental particle. Here's someone describing his school of thought. The worlds are formed when atoms fall into the void and are entangled with one another, and from their motion arises the substances of the stars. It sounds like gibberish to me, but the important thing is that he used the word atoms, or in Greek, atomos or atomoi, which means uncuttable. He believed that there were fundamental particles making up matter. About 2,000 years later, the physicists Binnig and Rober were actually able to visualize these fundamental particles, these atomos or atoms, using something called scanning tunneling microscopy. You're able to scan over the surface of an extremely smooth object and visualize individual atoms as seen on that picture. So Democritus was right in some sense. He was wrong in another sense though, because we know we can break up the atom, as we learned very vividly in the Second World War. So we need a revised definition of what an atom is if it's not indivisible. We define an atom then as the smallest part of an element that can still be recognized as that element. So we can break it down smaller, but it becomes unrecognizable as that element. Let's look at an analogy with pizza. We have pizza here. We have pizza here. We have pizza here. We have not pizza there. So we get too small and it's no longer pizza. It's no longer recognized as pizza. Here we have carbon. We have smaller pieces of carbon. We have an atom of carbon. If we go any smaller though, we have not carbon. We have an electron. So the smallest unit recognizable as carbon would be the atom of carbon. But what are the subatomic particles though that make up the atom? That's the important thing we're going to look at in this lesson. Subatomic particles. So we have two sets of subatomic particles, or two places where subatomic particles are located. We have here, which is the nucleus, and then we have the electron cloud surrounding the nucleus. In the nucleus we have protons, neutrons, and electrons. You should already know this from elementary school chemistry. Okay, what are the charges and masses of protons, neutrons, and electrons? I'm going to show you some scary numbers now. Scary number, scary number, scary number, scary number, scary number. You don't have to remember these. They're all on page 3 of your data booklet. Okay, the important things we have to remember are relative charges and masses. So the proton has a relative charge of +1, the neutron of 0, and the electron of -1. So the electron is the exact opposite of the proton in terms of charge. In terms of relative mass, we have 1, 1, 0. So these two guys, the protons and the neutrons, are similar or exactly the same. Well, physicists will tell you they're not exactly the same, but they're similar enough that we can think of them as the same in terms of their mass. The electron, I said 0, but it's more appropriate to say negligible, because it's about 1 out of 1,836 times the size of a proton or neutron. So you need about 2,000 of them to make up one of these guys. Based on these, we can get some definitions. What's an atomic number? An atomic number is the number of protons in the nucleus, and it determines the identity of that element. We'll talk about that in a second. The mass number is the number of nucleons. There's our new word, nucleons. Nucleons means protons plus neutrons. Okay, and it's similar to the atomic mass, which we'll also talk about soon. So let's try and apply these principles. We need to identify the element and deduce its mass and charge. Okay, so let's try that. What's the atomic number of this element? Remember, the atomic number is the number of protons. How many protons there? 2. Now, what is the X sub Z notation? What do I mean by X there? X is just the symbol of the element. So the symbol of the element which has an atomic number of 2, we look at our periodic table and we see it is helium there. So the symbol is helium. Okay? And sub Z, what is this sub Z? Z actually stands for atomic number. Okay? That's annoying that Z stands for atomic number. It comes from the German Zahl, which translates to number. Okay? You can remember it by thinking of this hippie lady here who says your zodiac sign, your Z sign, is the most important thing about you. It defines you. Similarly, the Z number, or the atomic number, defines an element. Okay? All right. Now, what's the mass number of this nucleus here? It's 4. And what's the charge? To determine that, we note that there are 2 protons, plus plus, and 2 electrons, negative negative, which means protons and neutrons perfectly cancel out for a net charge of 0. Nice and easy. Oh wait, sorry, not nice and easy. Our X sub Z notation we were trying to do here. So X sub Z is He sub 2. Okay, there is our X sub Z notation, He sub 2. It's kind of redundant because the sub 2 tells you it's He, and the He tells you it has to be 2 protons. But sometimes we still represent them like that. Let's do another example. Here we have 3 protons, so atomic number of 3. The X sub Z notation, if it has an atomic number of 3, it must be lithium, so we put Li sub 3. The mass number is 5, because we have 5 things in there. The charge must be, let's see, we have 3 protons, 3 plus, and 2 negatively charged things, 2 minus. Therefore, we have a charge of plus, or 1 plus, better said. Try this one on your own. In 3 seconds, I'll give you the answer, so pause it and think about it. 1, 2, 3. There's your answer. Let's look at ions. What are ions? We define an ion as an atom or a group of atoms with a net charge, Let's see what we mean by that. Here we have 3 different hydrogen atoms, okay? And we're going to indicate the X sub Z plus or minus notation. What is plus or minus? That's just the charge. So here we have H sub 1, of course. And do we have a charge here? Well, we have 1 proton, 1 electron. So we have no charge. We just leave it like that. The next one, though, we have H sub 1. But now we have 2 electrons and just 1 proton. So the electrons overpower the protons by 1 place. And since the electrons are negatively charged, they went out there. And then here, we have no electrons, so the proton wins out, plus. So those are 2 ions, those latter 2 things there. We call negatively charged ions like this, we call them anions. You can think that the N stands for negative. And we call positively charged ions like that cations. You can think that T in the middle of the word cation looks like a positive sign. All right, you go ahead and try these ones then. Pause the video and think about them. In 3 seconds, I show you the answer. 1, 2, 3. There you go. Finally, let's talk about isotopes. Isotopes are different atoms of the same element. That means they have the same atomic number. Remember, your Z sign or your atomic number determines who you are. So they have the same element, but they have a different mass number. Okay? So let's try some of these. Here we have 3 different types of hydrogen. And let's annotate these types of hydrogen. So here we have an atomic number of 1, atomic number of 1, atomic number of 1. That's the number of protons. How about the mass number? Here we have 1. Here we have 2. There we have, 3. Okay? So it looks like you can have the same number of protons, but different numbers of neutrons, right? 0, 1, 2 there. And that changes your mass number. Now, there's a new type of notation I'm introducing here, the X superscript A sub Z. Remember, Z is atomic number, A is mass number. So we put in the element symbol H sub Z1, and the mass number up there, 1. Here we have H, 1, 2. Here we have H, 1, 3. Okay, those are 3 different isotopes, of hydrogen. sometimes isotopes get special names. For example, we call this isotope deuterium and that one tritium. But it's important to remember that they are still fundamentally just hydrogen. Okay, that means their chemical properties still resemble fundamentally those of hydrogen. For example, all three of those types of hydrogen can form H2O water. And you might not know, if I gave you a cup of water, whether I was giving you regular water with the regular hydrogen, or what's called heavy water, which has deuterium. It's actually not that much heavier than regular water, okay? Because it still looks the same, it tastes the same, it has very similar chemical properties. If you put some sodium into it, the sodium would catch on fire, for example. The reason why isotopes have similar chemical properties is that chemistry is fundamentally a game of electrons, okay? The protons are important because they attract the electrons, but the neutrons just kind of hang out. The neutrons don't interact with electrons. So electrons do most of the chemistry. Protons are important because they attract those electrons. The neutrons don't really do anything. If you're thinking about neutrons as a chemist, you probably are a nuclear chemist, which is a special type of chemistry. Okay? Isotopes do affect, though, the physical properties. So it affects the weight or the mass of different atoms or elements, right? For example, deuterium will be twice as heavy as regular hydrogen, right? Because you have two massive things in the nucleus versus one. Okay? And because they have a higher mass, they also have a higher density, which is just mass in a given volume. And they also have a higher melting point and boiling point. So heavier isotopes would have a higher melting point and boiling point than lighter isotopes. Why is that? Well, if you're heavy, it's going to be hard to shake and break off the sort of intermolecular bonds that are holding you down as a solid. And so it's hard to boil to become melt to become a liquid, or boil become a gas. By analogy, ostriches or emus, large birds, struggle to fly, or peacocks, whereas smaller birds do not struggle to fly, right? Okay, how about you try these isotopes here? Try and annotate them with the X superscript A sub Z notation. Okay, figure out the atomic mass number and the actual element that is being illustrated here. I give you 3 seconds and I'll show you the answer. So pause the video and try it. 1, 2, 3. There are your answers. Okay. Here's another question for you. I'll give you 3 seconds to pause it and read it, because in 3 seconds I will show you, well, I'll show you a clue first actually. 1, 2, 3. There's a clue. Now in 3 seconds I show you the answer. 1, 2, 3. There's the answer, C. The number of electrons should be the same as the number of protons in a neutral atom. Okay? That way they balance out and the atom is neutral. Here's another one for you. 3 seconds, I give you a clue. 1, 2, 3. There's a definition. Pause it, think about it, because in 3 seconds I give you the answer. 1, 2, 3. The answer is B. So here we have two different isotopes. As you can see, the mass number changed, but the atomic number stayed the same. Fundamentally the same type of atom, different numbers of neutrons. This one would have 6 neutrons. 6 neutrons, 7 neutrons, okay? Because 6 plus 6 gives you 12, 7 plus 6 gives you 13. All right, let's do some practice. Now we're getting to the real things. These are the things you'll get on the exam. How do we do them? Complete the table below. I'm not going to read the instructions. You can read them if you like. You should read instructions on your exam though. Okay, so this is chlorine, obviously. It's chlorine, blah, blah. Number of protons here must be 17. Because the Z number is a subscript there, right? The number of neutrons is not explicitly given to us, but we can work it out. If we know this thing here is protons plus neutrons, and this thing here is neutrons, right? Then to figure out protons, we just take this and subtract out, sorry, no, I just confused you. This thing here is protons. So we take this and subtract out the 17, so 35 minus 17 is equal to 18. That's the number of neutrons. Okay? So mass number minus atomic number gives you number of neutrons. Very simple. Number of electrons, well, it's a negatively charged ion, which means that the electrons overpower the protons by one place. There's one more electron than the number of protons, which means if we have 17 protons, we must have 18 electrons. Okay, next one, lithium. Well, that's the name of the element, it's lithium. Number of protons is 3. Number of neutrons, can you figure it out? 7 minus 3, 4. Number of electrons, can you figure it out? It's positively charged. We have 3 protons, which means the protons are overpowering the electrons by 1 place. So we must have just 2 electrons. All right, so 3 is overpowering 2. 3 protons, 2 electrons. What is this element? X. It has 12 protons. Well, I will tell you that an element with 12 protons must be magnesium, Mg. Okay, but you should check that on your periodic table in the context of the exam. How many protons? It must be 12. How many neutrons? 24 minus 12 is 12. How many electrons? It has a 2 positive charge, therefore the protons are overpowering the electrons by 2 places. Therefore, we must have 10 electrons. Okay, cobalt. How many protons? 27. How many neutrons? This is one of those that we don't have enough information to figure it out because we don't have the mass number. So we don't know how many neutrons plus protons. So we just leave it there as blank. Okay, how many electrons? 27 protons and 3 plus charge. Therefore, who's overpowering who? The protons are overpowering the electrons, which means if there are 27 protons, there must be 24 electrons, ladies and gentlemen. Oh, these are getting long. Okay, I'm going to speed up now, okay? You can play it at 0.75x if you can't follow me. That is neon. Neon is element number 10. It must have 10 neutrons. And since it's neutrally charged, it must have 10 electrons as well. Okay, so this and this must be equal in a neutrally charged ion, in a non-charged species. Okay, so boron here. Boron is element number 5, I think. Correct me if I'm wrong. 11 minus 5 is 6. And the number of electrons, well, let's see, we have a sub 5 here. So the 5 is overpowering the electrons by 3 places. We must have 2 electrons only. Finally, the X there, X sub 35, that must be bromine. And we don't know its mass number, but we do know, okay, the number of protons. We don't know the number of neutrons. We leave that blank. We can't figure it out. It's one of those values that cannot be worked out. The number of electrons must be 36, right? Why is it 36? Well, we have 35 protons and a net negative charge, so the electrons are winning. And therefore I say, okay, the electrons are winning, therefore they must be up by 1 relative to the protons. Or you can do the math. I don't recommend setting up equations for these because it gets, I think, more confusing. Just do it the way I do it. Actually, leave a comment and tell me which way you'd rather do it. All right, your turn now. So pause this and try and work through all of them, or just pick whichever ones you want to do. Because in 3 seconds, I will show you the answer. 1, 2, 3. There are your answers. Let's do some harder ones. We have a carbon-12 anion with a single charge, and we need to write the nuclear notation for it. How do we do this? Let's see. So it's carbon. That's C. If it's carbon, it must be C sub 6. And superscript of 12, carbon-12 just means it's the isotope with 12 nucleons. Okay? And it has a single charge. That single charge is negative because it's an anion, therefore must be negative there. Done. Sodium is Na. Na stands for natrium, which is the word for sodium in Latin or Greek, I think. Latin? Latin? Yes, Latin. All right, it's a sodium is element number, I don't know off the top of my head, 11. Okay, sodium 23. The electron configuration of neon, that's an interesting one. So here's sodium here. It has 11 protons, but it has the electron configuration of neon, which has 10 protons. So a neutrally charged neon would have also 10 electrons. So we're expecting that the sodium has 10 electrons. If it has 11 protons, whoops, sorry, I'm writing an H instead of 11. If it has 11 protons and 10 electrons, then it must have a net positive charge, right? Net positive charge. Because it has 1 more proton than it has electrons. Okay, more. Oh, just a proton. You've seen this one before. It's just a hydrogen. Sub 1, superscript 1. And since it has just 1 proton, no electron, it must be positively charged. an ion of platinum with a mass number of 195 and 74 electrons. This one's a bit tricky. So platinum, we need to look on our periodic table, look for platinum. There it is, PT 78. Okay, so PT sub 78. Okay, mass number of 195 we put up there. 74 electrons, so the protons overpower the electrons by 4 plus. Okay, a bromine anion with 45 neutrons and a single charge. So bromine, wait, let's see. If it's bromine, it must have 35. Let's see, bromine 35, yes? 35 protons. And with 45 neutrons, the mass number must be 35 plus 45. We squish them together, we get 80. And the charge is a single charge, a negative there, since it's an anion, N for negative. Finally, we have an atom with 35 protons. That must also be bromine. It has 46 neutrons. 35 plus 46 would give us 81. And 35 electrons, so it's neutrally charged, so nothing there. And that's done. So now you try this set of them. Pause the video, because in 3 seconds I will show you the answer. 1, 2, 3. There's your answer. Okay? And that's it for this video. I'll see you in the next video when we will talk about I don't remember what we will talk about. So you just have to hang on and see. All right, that's all, folks. I'll see you. Bye-bye.